Hi, hi everyone. Hope you're doing well and having a great learning journey so far. I believe, you most of you must have attended the data preparation 101 session last Saturday, where our speaker has covered several aspects related to data preparation. And if you haven't watched the session yet, then head over to our your bootcamp dashboard, or you can also watch it on YouTube. With that, let me take this opportunity to invite you all and welcome you all for today's session, where we'll be building our very first classification and regression machine learning models for the bootcamp. And the session will be delivered by Farhan Mohammed. He has been our coach in the past, and he usually guides and mentors learners, and he has been an amazing coach in the last couple of boot camps. And he currently works as a data scientist at PayPal, where he is responsible for developing cutting edge fraud detection models using state of art machine learning and data mining techniques. With that, I'll hand over the session to Farhan. Farhan, it's all yours now. Thanks a lot for joining in.
Thank you, Chanukya. Hello, everyone. Good morning, good afternoon, good evening, in whichever part of the world you are. It's happy to be back here with DPhi. I've been part of DPhi for the first batch as a mentor, and it has been a great journey personally for myself as well as for all the learners who benefited out of this program. And I look forward to working with this team again and help the learners as much as possible. And it's great to see the way the community has grown and extended to so many people out there. So with that, let me start the session. So today's session will be on supervised learning and how to build your first regression and classification model. So just to give a small background, supervised learning is one of the most common techniques used in machine learning today. In fact, the new machine learning practitioners who usually begin their journey start with supervised learning, including myself when I started out. So it's a very important topic, and I wanted to focus in this session about supervised learning, like just give some background what it is and some important keywords that one must be aware before jumping into the problem statement. And then I will definitely walk you through building your first regression and classification model. Okay, I hope you're all able to see my screen.
Yes, yeah.
Okay.
It's visible. Yeah.
Nice. So yeah, so supervised learning, as the name suggests, it is basically designed to learn by example. So you can think of it as a teacher trying to supervise a group of students in a class, right? The teacher is explaining you something, so you're learning in the process, and then later you can apply whatever you have learned on your exam, let's say. So you can see that clearly it's like a supervised process where you're learning by examples and then you're implementing whatever you have learned out there. And also another thing to note is that supervised learning usually consist of input output pairs. That means in your data set you're given input data, and you're also given the examples or the output data that you can learn from. So this input output pairs can be used to train a model to learn the patterns in the data. Also here we have a defined target variable, right? So this target variable along with the input variables is the main crux of what supervised learning is all about. So mainly supervised learning is used to resolve two types of problems. One is classification and second one is regression. So let's go over one of each of them in detail. All right. So as I mentioned, there are two types of problems that supervised learning problem deals with. First one is regression, and second one is classification. So in case of regression, the output or the target variable is going to be a continuous value or a real number. For example, let's say we come up with a question: what is the temperature going to be tomorrow? So just looking at this question, you can think of the answer to be a continuous value or a real number, right? It can be like 84 degree Fahrenheit, or it can be like 20 degrees Celsius. So it's basically a continuous value. So you should think of it as a regression problem. Similarly, in case of classification, the output variable is going to be categorical, right? It has a fixed set of classes. So let's say the example could be, will it be hot or cold tomorrow? So here we only have two fixed classes. It can either be hot or it can either be cold. So just by looking at the nature of the output variable, you would able to tell that this is a classification problem. So I hope the distinction is clear, because it's very important that one understands how to differentiate between a regression problem and classification problem just by getting an understanding of the overall data. So let's look at some more examples of what a classification use case can look like and what a regression use case can look like. So in case of classification, as I mentioned earlier, it's the goal is to classify the outcome. So the examples can be, let's say you want to predict whether a transaction is fraud or not fraud, right? So you have a transaction data and you have set of input features, and you want to predict whether the future transaction is going to be a fraudulent transaction or not fraud. So here the goal is to classify the outcome into two classes. So it's a classification problem. Similarly, let's say you want to predict whether to give loan or not to an applicant. Again, here we are trying to categorize the outcome into two classes, whether to give loan, yes or no, right? So it's a classification problem. Another example could be predict whether to give college admission or not. Again, this is a binary problem where your output consists of only two classes. And next, we have example like predict the grade. So the grade can be A, B, C, or D. Again, it's a categorical variable. It only has four fixed classes. So this kind of problem is known as multi-class classification problem, because here you have more than two classes, but again we have only fixed set of classes. So this problem again comes under classification. So as I mentioned, the classification can be two or more than two. So when you're dealing with two classes, it is known as binary class problem. And when you're dealing with more than two classes, it is known as a multi-class problem. Next, coming to the regression. So regression is the problem of predicting a continuous number or a numeric value. So the example can be, let's say you're trying to predict the house prices based on some input features like square feet of the house, location of the house, number of bedrooms, number of bathrooms. So based on that, you want to learn from the previous examples, and you want to predict the house price for the future future inputs, right? So here the price can be a continuous value. It can be like $100,000 or $500,000. So it's basically a continuous value. So it's a regression problem. Also, let's say you want to predict the crime rate. So again, this is a rate that can be a continuous value. So again, it comes under a regression problem. So let me show you what a typical machine learning workflow might look like in general. So the first step in any data science problem when you're dealing with is to first get the data, right? So it's a data acquisition phase. So here the data can come from several different sources, and also your data can be structured data or not non-structured data. So so once you have your data, once you have your data available, the next and most important step in the data science workflow is data cleaning. So this is very crucial step, because most of the time in real world, when you're dealing with real world data, the data consists of a lot of inconsistencies and errors that you might need to deal with, such as you might need to handle the data types. It might, because the data types might not be consistent always. Then you might also need to deal with missing values and impute the missing values, because the machine learning model does not handle missing values by default. Similarly, you need to handle categorical features and encode them into numeric format so the machine learning model can interpret that. and there can be also duplicate rows in your data set. So there can be several factors that needs to be considered, and in fact most of the time spent by data scientists is actually in the data cleaning phase. So this has to be done explicitly and manually in your data science process. So next, once your data is cleaned and it is properly in the shape that the machine learning model expects it to be, then the first thing that you would be doing is to like split your data into train, validate, and test. So the trained data set here is basically it is used to train the model on the existing observations, right? And the test data set is basically you can treat the test data set as a replica of future data that the model has not seen during the model training. So it is essentially very important to make sure that you're always splitting your data set into train and test at a minimum in order to ensure that you might get a better estimate of the model performance when you're testing the performance of your model. So if you do not split your data into train and test, and if you, let's say, just combine all of your data and just train a model, then you later try to test it on a portion of the trained data, then you're essentially doing something which is known as data leakage, because you don't want your future information from tests to be present in your trained data. So it is essentially very important to split your data set into train and test beforehand, and just use your trained data set to train your model, and then use the trained model to generate predictions on your test data set and evaluate the model. So you might be surprised looking at the second split, which is validate. So you can just think of this validate as a way to uh, get a better model. So this validate data set is comes from the subset of train, where you basically like evaluate the model performance on a portion of train data set called validation set, and you try to get the best model based on the hyperparameter tuning. So in this exercise, we will only stick to like train and test for simplicity purpose. And once we split the data and we train the model on the train and we generated predictions on our test data set, then we will use the predictions and the actual value from the test to evaluate the model performance. And once the model performance is evaluated and you're confident about your model, then the model can be deployed to the production or any stage that you're interested in. So I hope the workflow is clear. Okay, now let's talk about some of the important key terms that you might often hear when you're dealing with a machine learning problem. One of them is called label or target variable. So both of them can be used interchangeably, but essentially it's nothing but it's going to represent the output column in your data set, and this is the column that you're trying to predict on. So let's say in the example of spam detection, the label or the target will be the category that the email belongs to. That is whether the email will be a spam or not spam. So let's say in the spam detection example, you get a new email, and your email system has a spam detection classifier in place. So as soon as you get a new email, the the spam detection classifier will run the model predictions on the new email, and generate a prediction whether this email is falling into a spam category or non-spam category. And based on that, you might see that the email sometimes goes to spam and sometimes it will remain in your general category. So this is how a model will try to classify the inputs in real time, and you'll get an output value basically. Next, let's talk about one more key term which is very common, and you might hear different terminologies, but like don't get confused, because usually you might hear people saying often different things, but it basically the predictor or input variables or features, these basically mean the same thing, and they represent the input features that is available in your data set. Um, and they are also sometimes called as predictor variable or independent variable. Um, And let's say in the example of spam detector again, the features could be something like this, right? It can be words in the email text, it can be sender's X address, it can be time of the day the email was sent, or it can be an email which contains certain phrase. So these are all the input data, and using this input variables or predictor or features, you're going to predict the target variable. Okay, so I just wanted to give another example here to show you how a typical real data might look like. So as you can see here, this is an example of standard metropolitan areas data set. And the target variable that we are interested to predict is crime rate. So as you can see, this is our target variable or the target feature, and the land area, percent city, percent senior, physicians, hospital beds, graduates, workforce, income, region. So all of these are our input variables or input features. So basically, we will be using the input features to train a model and generate predictions on the crime rate target variable for future data. All right. So in this slide, we are going to talk about what is train test split and why is it essential. So we have already looked at on a high level why do we need a train test split. So again, like training set is basically it is used to train the model on the existing observations in your training data set, and test set is basically you can think of it as a replica of the future data that the model has not seen during the model training. So always when you're dealing with any kind of data in supervised machine learning problem, you have to split the data into train set and test set. So for training set, you might basically consider like 70 to 80% of the portion, and for your test data set, you may consider maybe 20 to 30%. So once you divide the data into train and test, then you need to use the training data set to train the model, and test data set will be used to evaluate or test the model to check the performance. So in this session, as I mentioned, for simplicity purpose, we might only be splitting it into train and test. But in general, in often real world problems, you might also find another split called as validate, which is basically used to get a better model. All right. So with this, we have covered most of the basics that we need to know about supervised machine learning algorithms and the key terminologies. With that, we should be able to dive into the notebook, and we will walk through the how to build your first classification and regression problem. All right. So in this session, I will briefly cover a walkthrough of one classification and one regression problem. We will learn how to load the data, how to quickly visualize the data, get the summary statistics of the data, how to do a train test split, and basically how to choose a model and build a model and evaluate the performance and look at the results of the model. So we will be doing it for two examples, one for regression and one for classification. Since I've already covered the basics of what is supervised learning and types of supervised learning, we can directly jump into the code walkthrough, but you're free to always look at this as a refresher. All right, so for classification model, let's start with loading the data sets into a pandas data frame. So as you can see here, importing two statements: import pandas as PD, import numpy as NP. So pandas is a data preparation library or data manipulation library, which can be used to prepare your data, like clean your data and do any kind of structuring or formatting on top of your data to get it into a shape that the model can understand. And NumPy is basically a mathematical library where you can perform certain mathematical computations. And the data that we will be using today is iris dataset. This is one of the common datasets that you might find in the public datasets. And this data has already been uploaded to the DPhi official page. So you can directly use this link in order to read the dataset. And the way that we read the dataset is using the pandas read underscore CSV method. So let me run this cell. Okay, now that the data has been loaded into our memory, let me print the shape of the data to see the number of rows and columns, and also let's look at first 5 samples of the data frame. So as you can see, there are 4 input features in this data frame, and there is one output column called as variety. Also, one thing to note that you can see that the input features are numerical just by taking a glance at it, and the output variable, which is variety, is a categorical feature. So we will also briefly look into how many classes are available in categorical variable in that output feature and try to understand that. So now that we have loaded our data set and looked at the shape of the data set, we can clearly see that there are 150 rows and 5 columns in the data set. Now let's look at examining the data types of this data and whether there are any missing values or not. So the best and easiest way to examine the data after loading is using the dataframe.info method. It's a quick way to assess the data summary by analyzing the data types and non-missing values in each of your column. So let me run that on top of the iris data frame. So as you can see, it gives us a table-like structure where you have a list of columns, then you have the non-null count for that column, followed by the data types. So among the data types, you can clearly see that for the first 4 columns, the data type is float, which is nothing but it represents a numerical value. And then the target variable variety has a data type called object. Also, it's very important to look at the missingness in your data. So since we have already looked at non-null count and we observe that there are no null values, let's also, I just wanted to show you a better way of looking at null value by taking the sum of null values in each of the columns. So the isNull method is basically it gives you a Boolean value, whether a certain value in your data frame is a null value or not, true or false. And by applying sum on top of that, we are basically summing together or adding together all the null values in each column. So again, as you can see, there are no null values in your data set. So you don't have to explicitly handle this portion, but most often in real world problem, you might deal with missing values. So you need to impute the value either with mean or mode, depending on the type of problem that you're dealing with. Okay, now we can move on and basically generate some descriptive statistics on the data. So descriptive statistics can be very important, especially when you want to understand especially when you have numerical features in your data set and you want to understand how the distribution looks like, what is the mean value, what is the standard deviation. So the describe method in pandas is one of the very useful method that will give you a lot of summary statistics about the data. So let me run this cell, and as you can see, for each of the columns, it is printing what is the count of observations or count of rows in your data, what is the mean value for each column. So for sepal length, you can see that the mean value is 5.8, for sepal width is 3.05, for petal length is 3.75, and for petal width, it's 1.19. Similarly, it also gives you the standard deviation for each of the input feature, the minimum value, and also values at 25th percentile, 50th percentile, and 75th percentile. And it also gives you the maximum value which is available in your data set. So since the input features in iris dataset represents the measurements in centimeter, these are basically measurements of a flower. You can see that the maximum measurement for this particular feature is 7.9. The maximum measurement for sepal width is 4.4. The maximum measurement of petal length is 6.9, and for petal width it's 2.5. Next, we are going to get the counts of unique classes in our target variable. So you can achieve that using the group by function. So you can pass in the variable that you want to group by, and then on top of that, you can do any aggregation. So in this case, I wanted to print the number of observations in each of our target category. So using the group by and dot size method, we will be able to get the size of the unique classes in our output variable. So let me run this cell. So as you can see here, the target column variety consists of three classes, Setosa, Versicolor, and Virginica. And if you remember, the data frame consists of 150 rows, and all of these three classes in our output variable is equally divided. So we have 50 samples of Setosa, 50 samples of Versicolor, and 50 samples of Virginica. So these are basically three different species that we are trying to predict on for a given flower measurement. And similarly, similar to how we got the size of the classes, we can also obtain the mean value for each category in our target variable. So this can be obtained using the group by method again, and just passing dot mean function. So as you can see here, for each of the output class, we have the mean measurement for sepal length, mean measurement for sepal width, mean measurement for petal length, and mean measurement for petal width. We can similarly obtain the mean measurements for each of the three classes here. So this gives us a high-level summary, and it helps us understand, get an idea and insights about the data that we are dealing with. So you know that this is the average value, this is the maximum value. So it really helps us get a brief insights about the data that we are dealing with, which is one of the most important things. It can also come under data visualization. So always make sure that you run some kind of summary statistics, get a brief idea about the data that you're dealing with, the data types, and get summary statistics of the data, try to understand the average value, the maximum and minimum values, to get a high level understanding. So now that we have already loaded our data set, we evaluated the missingness in the data, we evaluated the data types, and we looked at the summary statistics of our data. Let's move on to splitting our data set into train and test. So for this exercise, we will be splitting our training data set into 80% and the test data set into 20%. So as to again give a quick refresher, the model will be trained on the trained data set, which is the 80% of our data, and then this model will be used to predict on the 20% of the test data, and also evaluate the performance on that data to generate by generating metrics, right? So let's move on, and let's split our data sets into train and test accordingly. So for splitting the dataset into train and test, we use model selection package from sklearn library. Here, as you can see, I will be using the model selection dot train test split method. So this train test split method is again one of the important methods which is available in model selection package that you can call, and inside that you can pass in your data frame that you want to split upon, and the test size or the portion of the data that you want to hold out for your test data set. And I wanted to pass it to variables called iris train and iris test. So once I do that, next step is to print the shape of the original iris data. And then let's also print the shape of the training dataset, which is iris train.shape, and the test dataset, which is iris test.shape. And once we split the dataset into train and test, you should always reset your index. This is because your ML model expects that your input data is in a proper index format. That means your observation starts from 0, then followed by 1, 2, and so on. So when you split your data into train and test, the samples will be split in a random fashion. That means your index might be shuffled in this case. So you always need to make sure that once you do the split, you should always reset the index so that the index always starts at 0. So we do this for both the training data and the test data.
Farhan, one quick thing. Can you zoom
Yes,
in a bit, a little more?
sure.
Yeah,
Yeah.
yeah. And also maybe you can, yeah, yeah. Yeah, this is perfect. And maybe a little
Okay.
louder. I think that should be fine. Yeah,
Okay, sure.
yeah, yeah. Yeah. Great.
Yeah.
Thanks.
So yeah, as I was saying, in this step, we basically split our data set into train and test. For train, we used 80% of the original data, and for test, we are using 20% of the original data. And once we do the split, we want to check the shape of the original data and also the shape of the training data and shape of the test data. So this is to make sure that we are splitting the data in a correct manner. So we want to compare the number of rows in our data set before splitting and after splitting. And also one thing to note that we always need to reset the index for the train and test data set after we split the data, because the machine learning model expects your index value to start at 0. So we need to make sure that we split the data and then reset the index of our data frames. So let me run the cell, and as you can see, the shape of the original iris data, it's 150 by 5, and the shape of the train data is 120, and shape of the test data is 30, because we split the train into 80% and test into 20%. So now that we have split our data into train and test, we can move on to feature selection. Okay, so why do we need feature selection? So let's take an example. Let's say in your data frame you have 100 rows and 10 columns, and you use all of the 10 columns to train a machine learning model. So when you use all of your features in your model, it doesn't necessarily mean that the model will perform better or the model will learn better from the data, because the quality of the model does not depend on the number of features that you're feeding it into the model. Instead, it depends on the quality of the features itself. So you need to make sure that you need to assess the quality of the features that is going into the model, because if there are low quality features in your data which may contain noise or irrelevant patterns, it might negatively impact the performance of the model. So it is utmost important to ensure that you assess the quality of the data and make sure that only the features which absolutely are relevant goes into the model. So this process of basically selecting the most relevant features from your input data and feeding it into the machine learning model is called feature selection. And one of the common problems when you're dealing with real world problem is you come across a lot of features. You might have hundreds or thousands of features, and and if you do not do proper feature selection and use all of these features to build a model, then you might come across a problem known as curse of dimensionality. So this basically curse of dimensionality means that your matrix of data is huge or it's sparse, and the data that you're feeding it into the model is not statistically significant. So the results that you're going to obtain from your model is also not going to be statistically significant. So therefore, it is very essential to quality control the data that is being fed to the model. And there are several feature selection methods out there, but I have just listed like some of the most popular ones, which is correlation coefficient, variance threshold, recursive feature elimination, lasso regression, and random forest importance. So we will be only looking at two feature selection methods, two of the simple feature selection methods in this session, but you can give a read about the other feature selection methods which are out there, which are more advanced in nature. So let's implement the feature selection algorithm here. So as I mentioned, for iris dataset, we will be using one of the feature selection methods, which I talked about, which is called variance threshold. So the goal of variance threshold is basically to filter out or to remove the low variance features. So what is the intuition behind removing the low variance features? So basically, your machine learning model expects that the input features that you're feeding it into the model has some level of variance between them, because you don't want to feed in similar features which carry the same amount of information. That will not help the models. It might sometimes negatively impact the performance, because the model might overfit on those features. So you need to make sure that the features that you're actually fitting to the model have high level of variance. And the variance threshold method basically removes the features which fall under a certain threshold criteria. So let's say if the variance of a certain feature is below 0.2, so you can specify that in the variance threshold, and it will filter out all of the features which falls under the 0.2 threshold cutoff. Scikit-learn provides a very easy implementation of variance threshold function, which can be applied to any data set. So let's look at how it can be implemented. So one thing to note is that the variance threshold function is only applied to the input features. So it cannot be applied to the output feature. So for that reason, we need to first drop the output column or the target variable from our data set. So let me do that. So here using the drop method, I drop the variety, which is our target column from my data set. And then just let's verify the shape of the data. And you see that we have only 4 columns left in our data set. Now let's apply the variance threshold method. The variance threshold is available in sklearn.featureSelection library. You can import the library, and first step is you need to create an object of variance threshold. So you can do it by a variance threshold. Just call the same method. So basically you have loaded the object of variance threshold class, and then then in order to apply the variance threshold on our data frame, we need to apply something which is known as fit underscore transform. So let me tell you what this fit underscore transform is doing. Basically, fit is nothing but it is trying to calculate something in your data frame. So in this case, we are trying to calculate the variance of each column in your data set. And then the transform method in combination will transform your data set into the required variance. So first it calculates the variance, then it will apply the threshold to the variance. So let's say if you specify a certain threshold, then it will also filter out the columns or drop the columns from your data frame. So here we are just applying fit underscore transform on our data frame, but just note that we are not passing any threshold parameter here. So by default, the threshold is 0, so it will not drop any records from the data set. So once we apply that, let's just print the features as well as the corresponding variance value for this data frame. So as you can see here, the sepal length, the variance of sepal length is 0.68, variance of sepal width is 0.18, variance of petal length is 3.09, and variance of petal width is 0.57. So we can also, visualize these results using a bar chart, which is more intuitive to just understand which of the columns had a high variance and which of the columns had a lower variance. So we will be using matplotlib library to plot the bar plot. So it comes with a bar plot function where you can pass in the x value or the horizontal axis that you want to show, and the vertical axis for which I want to display the variances for the input features. So let me run this cell, and as you can see here, this chart basically compares the variance for each of the input columns. So just by looking at the chart, you can observe that the petal length has a very high variance. So this is a good feature to go into the model, and you can see that the sepal width has a very low variance compared to the other features. So far we have only implemented the variance threshold to evaluate the variance of each column, but we did not necessarily drop the columns. So this time let's specify a threshold value and drop all the features for which the variance score is below 0.2. So we can do this by specifying the threshold parameter inside the variance threshold class. So I'm passing threshold is equal to 0.2 here, and then I'm going to fit and transform this on my training data set. And once we do that, let's also print the shape of our data set. Basically, the columns. The shape of one will give the count of the columns in your data. So let's print the columns in your data before applying variance threshold and after applying variance threshold. So as you can see here, there's only one column which sepal width, which is falling under 0.2 threshold. So we only expect that the variance threshold will only eliminate one of the columns from the data frame. So let's verify that. So as you can see here, the number of features before applying variance threshold was 4, and number of features after applying the variance threshold is 3. So in this case, we can clearly notice that the feature sepal width has been removed since the variance was falling below 0.2. So moving on, next step, we also need to split our data set into features and label. So if you remember, so far we have only split our data horizontally. So we have split our data into like 80% and 20% for train and test. Now, but if you want to build a model, we need to explicitly tell the model what are our input features and what is our target variable. For that, we need to split our training data set and test data set into input features and target variable. Okay, so here, as you can see, I'm specifying what are my input features going to be. So I'm only passing the 3 columns because the sepal width was dropped from the variance threshold after feature selection. And the label column is our variety column. And then here I'm printing the features and the labels. And then here I'm creating like new variables. Basically, it contains a data frame with only the input features. So iris train features consist of training data with only the input features. Iris train label consists of training data with only the output column. And then the iris test features consist of only the test data set with input features, and iris test label consists of a test data set with label column, the target column. So let me run this cell and let's look at what the features and labels looks like. So the features, we only have 3 features now, and there's only one label here, variety, and we have already split our data set into features and labels for both train data and test data.
Yeah. So, Farhan,
Yes.
just wanted to drop in so that I can we can ask some quick questions. I think people are
Sure.
having some questions around variance threshold, and
Okay.
before that, maybe like I'll just add some context because many of them are beginners, right? So
Yeah.
coming to feature selection, probably right now here we are probably having some 5 or 4 features, whereas there can be a case where there can be 100 features, 100 columns, right? Let's say like if we are dealing with fraud detection data set, then probably you end up having a lot of features, and you might want to you can't input all the features into the model. That's where like we would probably end up using feature selection. And not just that, even in smaller cases where you might end up having some 10, 20 features, you might not want each and every feature to be put onto the into the model, whereas you would want only those effective features which drives significant results to be fed into the model. So that's where like we'll be using the feature selection method. So that's some
Yeah.
context for the beginners. But before that, like probably you can add some context about variance threshold, and also I think people are having some questions on curse of dimensionality, and there is one more thing which was there. I think it's just you spoke about statistical significance, right? So these are the 3 things I think people have. Yeah, maybe if
Okay.
you can throw some light on those, that would
Sure.
be great. Yeah.
Sure. So let me start with the descriptive statistics, which is basically looking at the summary statistics of the data set. So as I mentioned, it is very important to understand the data that you're dealing with. So in this case, we are dealing with iris dataset, which consists of 4 input features, and these input features consist of numerical columns, right? So as you can see here, all these 4 input features represent the measurements of a flower in centimeters. So this for sepal length, the first observation has 5.1 centimeter, this has 3.5, this has 1.4 and 0.2. So, what is the goal of generating the summary statistics? The goal of generating the summary statistics is to get some aggregate view on your data set. So, you might want to look at different metrics on your data, like let's say for your sepal length column. What is the minimum value in this column? What is the maximum value in this column? What is the mean or the average value in this column? Right? And what is the 25th percentile, 50th percentile, 75th percentile? So to get a brief idea about what the summary statistics of the data, we need to do some descriptive statistics. So here we are using the describe method, which gives us a very high level view of the data set. Like it gives you an aggregate view. So let's say for sepal length column, it tells you like how many count of observations are there in your data set. So as we have seen, there are only 150 rows in your data set. So we have 150. And then what is the mean value in your sepal length? It's 5.8 centimeters. What is the standard deviation? What is the minimum value? And what is the maximum value, right? So this helps us to get a very high level view of our data set to understand the aggregation, like different metrics that you can collect from your data set. So it's often very useful to get this understanding when you're, especially when you're dealing with numeric data types. So I hope that answered the question. And coming to feature selection, so as I mentioned, like in real world problems, you might be dealing with like hundreds or thousands of features, and often you might need to implement more complex feature selection algorithms, and definitely the complex feature selection algorithms will be covered later in the learning session. But just to give a high level idea, let's say you have hundreds of features in your data set. You're dealing with a fraud data set, and you have like hundreds of features, and you want to identify the best set of features that you can use to train the model. So in order to do feature selection on top of this data, you might generally use some advanced methods. Let's say let me give an example of recursive feature elimination. So what recursive feature elimination does is it basically takes all of your input features, let's say your 100 columns, and it builds a model on top of that. This model can be a decision tree or a random forest, right? So it builds a model on top of that, and it will compute the feature importance for all of the columns. All right. So once you have the feature importance scores of all of the columns, it will basically remove the columns which have very low feature importance. So let's say you want to remove like 5 columns. So you can specify the value that we want to remove 5. So so now you are only left with 95 columns. And then you again run the model on top of the 95 columns. And again, you filter out 5 columns from that which are least important. And then again, you run the model. So it is like an iterative process where you're filtering out the features which do not contribute well to the model, right? So this is one of the sophisticated approach that can be used when you're dealing with a real world problem where you want to absolutely make sure that you're selecting the features which have utmost importance and which can add value to your model. So I hope this answers your question, but again, don't worry about the sophisticated methods because it will be covered in the learning material. For now, we just went with variance threshold. So let me again explain the intuition behind using variance threshold. So since in our data set here, we are dealing with like numerical data types, we need to we need to understand that some of these columns might have similar information. That means these columns do not have high variance between each other. They carry the same information. And we do not want our model to learn from the columns which has the same information, right? So we want to basically evaluate the variance in our data set to make sure that the variance level is high or the variance score is high for each of the column. And if certain columns have very low variance, that means they don't add any new information to the model. So we might need to filter those columns. So here in our case, we used a threshold 0.2 as an example, of course, to filter out one of the columns which falls under this threshold. So the sepal width has a very low variance. What does that mean? That means it is not much different from other features. That means it doesn't have varying information. It is basically carrying the similar information. So that's why we don't want to keep the same keep a column which has the same information. So we basically drop that column. So that's what the method or the function variance threshold is actually doing here. So I hope that clarified all of the questions, Chanakya.
Yes, yeah. Thanks, Farhan. I think
Sure, sure.
they did clarify. Yeah, thanks. Yeah, we
All
can move
right.
on. Yeah,
So I can move on, right? Okay.
yeah.
All right. So let's move on to the fun stuff, which is building your first classification model. So for the classification model, I'm taking an example of decision tree, which is one of the most commonly used algorithms, and one of my favorite algorithm when I started learning machine learning. So let me give a brief intuition about what is this algorithm about. So decision tree, first of all, decision trees is used to solve both classification and regression tasks. So it's not like it's only applied to one of the two problems. So it can be applied to either classification or regression task. And the goal of decision tree algorithm is to create a model that predicts the value of a target variable by learning simple decision rules from the data features. So let me break this down because sometimes it might be difficult when you hear about these terms, right? Like decision rules and all. So let's say you have your input features. Let's say you have 10 columns, and you want to and you have a target column that you want to predict the value on. So basically you train a model using the input features and also the output column, and the model will learn from this data and it will predict. So in decision tree, what happens is the model will create simple decision rules from the input features. So let's say, let's take this example here. So let's say the three attributes here, the has features, can fly, and has fins. These are your input features. Okay, this is basically an animal tree, which is trying to classify whether an animal belongs to one of the four classes: hawk, penguin, dolphin, or bear. Right. So the last row, this becomes your target variable or your output column, and these three are your input features. So what decision tree is trying to do is trying to create some decision rules that can lead to your target variable. So first thing is it tries to it takes a input feature attribute on which it wants to create a rule and split the rule into further conditions. So first thing it is checking is does this animal has feathers? Okay, so if the animal has feathers, uh, go into this node, and then if the animal has feathers, then it is checking can animal fly. If the animal can fly, then it is classifying the outcome as hawk. Let's say it's false, so animal cannot fly. So in this case, it is classifying it as a penguin. Similarly, let's say if the condition was not that the animal did not have feathers, in this case, it will go into the false branch, which is whether the animal has fins. So if the animal has fins, then it is classifying it as a dolphin. If the animal does not have fins, it is classifying it as a bear. So as you can see here, decision tree is trying to break down your input features and creating simple decision rules out of that by splitting the data into multiple rules or sub conditions, and then classifying your target variable into one of the categories in your target variable. So, in order to get it, so another point that I wanted to mention, which can clear a lot of things, is you can treat the decision rules as if then else statements. That means if this condition is true, then do this. Else do this, right? So we are basically treating them as if then else statements in a programmatical way. You can think of it that way. And also, the deeper the tree, the more complex the rules. So when I say deeper, it means we are basically breaking down into multiple rules, right? So the horizontal axis here means that it represents the depth of the tree. So in this case, the depth of the tree is 3 because we are only breaking it down into two subconditions, and then we are generating the predictions. So another thing that I wanted to explain is the terminology. So it's important to understand how a decision tree is built, but it is also more important uh, to understand, get an understanding of the different components that goes in building a decision tree. So the first one is called root node. So the root node basically represents the topmost attribute of the tree. So this is nothing but the topmost input feature that you have in your data set, and this is where the tree starts to split. And splitting is nothing but it is the process of dividing a node into two or more subnodes. So you can treat these boxes as nodes, and you're basically splitting the node into subnodes from your parent node. So you can treat this as a parent node, and you can treat this one as your child node. And then decision node is basically when a subnode splits into further subnodes, then it is called a decision node. So let's say the has feathers had split into two more nodes, right? Can fly or has fins. So these are the decision nodes which comes from the sub nodes. And finally, the last term to understand is the leaf node. So leaf node is basically the final node that you cannot split further. So this is also known as your class node, because this represents one of your output classes. So in our case, we are trying to classify the flower features into one of the different classes, whether it falls into setosa, virginica, or versicolor. So your leaf node would end up being one of the three categories. It can be setosa, versicolor, or virginica. So now that we have got a high level intuition of what a decision tree looks like, and what the different components of a decision tree looks like, let's jump into the implementation of decision tree. And just a note that I'm also adding documentation links for all the things that I'm talking about, so you can refer that material to get deeper understanding about most of these things. So let's look at the implementation of decision tree. So here, since we are going to apply decision tree for a classification problem, we will be using a decision tree classifier. And if we are going to apply this decision tree on a regression problem, then we would be using a decision tree regressor library. So in this case, let's create a model object. So we are first we imported the decision tree classifier. Then we are creating a model object of decision tree classifier. And here we have just passed a parameter, or it's called as hyperparameter, called max depth. So this max depth basically controls the maximum depth of the tree. So as we have seen here, this particular tree has a depth of 3, because it is split three times, right? It has three axes basically. So here we can basically control that depth. And the reason we do that is because it's part of model tuning, where we want to we don't want the tree to we don't want the tree to split into like a high depth, because if you split the tree multiple depth, then you might end up overfitting on your training data set. That means the model is learning like noise in your data set. So that's why we can, we need to do some level of tuning, where we can pass in a value, and we can always do hyperparameter tuning, where we can give a range of values of max depth, like let's say 3, 4, 5, 6, etc., and then it builds a model with each of the value and gets the best model out of it. But for simplicity purpose, we are not going to apply hyperparameter tuning. It will be covered in your later session. So for now, we will just build a decision tree model with a default max depth of 3. So once we created an object of model of decision tree classifier, we call it DT. Next, we are going to fit this model on the training data. Again, as I mentioned, fit is nothing but it is going to, so in this case, it is going to it is going to learn the mapping between the inputs and the outputs. And for that reason, we are specifying what are the input features, which is iris train features, and what is the label column, which is iris train label. So we are explicitly telling decision tree what is our input features and what is our target column. And once we fit the decision tree, let's run this cell. So here we can see that the decision tree classifier has been created, and these are all the default parameters that it shows. So now that we have our decision tree model trained, and the model has already learned the decision rules from your input features, let's use this train model, which is DT in my case, and predict it on our test data set, which is on the input features of our test data frame, right? So let's do this DT. So this can be achieved by passing dot predict method on your model object and passing in the test data frame, which consists of your input features. And once we do that, let's also create a data frame with the predictions that you're obtaining from your predictions DTs, because we want to see what is the predictions for each of the observations in your test data set, right? So this piece of cell will create a data frame on top of your predictions, and then it will rename the columns to DT underscore prediction to make it more intuitive. And then I'm printing the first 5 predictions of the model. So let me run the cell, and as you can see here, the DT prediction, this is the prediction that the model has made on your test data set, and these are the categories that the model has predicted to. So now you would be interested to know well whether this is a true value or whether the model has predicted this correctly or incorrectly. For that, we need to basically let's combine your the true label and your predicted label and look at the results side by side so that you can understand whether the model has made a right prediction or not, right? So for this, we will be using a concat function from pandas, and we are going to pass in the true label, which is the iris test label, and the predicted label, which is the iris spread label. And then we will be displaying the first 5 rows in our data set. So let me run this cell. So as you can see here, the first column represents the actual value of your data frame, and the second column, DT prediction, represents the predicted value. So as you can see here, the true value is versicolor and the predicted value is versicolor. And here the true value is versicolor, predicted value is versicolor. So the model has made good correct predictions for your first 2 observations. So similarly, you can visualize this for all of them. But let's go ahead and look at the accuracy of the model. Accuracy is basically the number of correct predictions that the model has made, right? So for that, we need to import accuracy score from metrics from sklearn.metrics library, and use that accuracy score and pass in our test label as well as our predicted label in that, and let's look at the accuracy value. Okay, so we can see that the accuracy is 93.33, right? So which is good. That means the model has made and the model has correctly predicted 93% of the time in this for the test data set, right? The model has made 93% correct predictions for your test data set. So sometimes just by looking at the accuracy score might not be very intuitive, because you want to understand for which observations the model made incorrect predictions, and you want to know like how many incorrect predictions are there in your model, how many correct predictions are there in your model. So for this, we would be using something called as confusion matrix. So as the name suggests, this terminology, this matrix can be confusing at first to understand, but once we get a deeper understanding, it can be much more clear. So basically, confusion matrix represents a table which is used to describe the performance of a classification model on a set of test data for which the true values are known. So since we are dealing with a classification problem and we already know the true value in our test data frame, and we just want to compare the performance of this true value against the predicted value. So for that, we will be using metrics.confusion matrix, and inside the confusion matrix, we would be passing in the true label and as well as the predicted label, right? So this is our true label in our test data, and this is our predicted label in our test data set. So now that we have created the confusion matrix, let's create a data frame with proper table index values. So which is nothing but the 3 classes that the model is trying to predict on. And let's create a plot of confusion matrix and visualize the matrix here. So okay, there seems to be an error. Okay, so I did not run the previous cell. So the metrics did not get imported. Now that the metrics is imported, let me rerun this cell. Okay, looks like I need to import the metrics library as a standalone function, since I'm actually passing here metrics.confusion matrix. So let me do this. Looks like there's one more library which is missing. So I will talk about what this library basically does. So we also need, sometimes on top of your matplotlib, if you're applying any kind of styling on your data, like some kind of color coding and all, you might also need to import a library called as cbon. So it's saying me that the library SNS is not defined, whereas I'm actually using this library in my data frame. So let me import that and then run the cell again. Okay, so now that you can see the matrix is being created, this is called confusion matrix. Let me try to understand, let me try to explain how this matrix looks like. It might be confusing at first, but let me do my best. So if you see here, this is, we are dealing with a multi-class problem. That means we are having three different classes. So on your horizontal axis, you have your true labels, where you have Setosa in the first axis, versicolor in the second axis, and Virginica in the third axis. And these three axes represents the true label for your target column. And then on your vertical axis, you again have your three classes, but it represents your predicted label for your test data set. So here, by looking at this confusion matrix, we would be able to say like how many correct predictions did the model make and how many incorrect predictions did the model make. So let's say, so one thing to remember is the diagonals in your confusion matrix represents the correct predictions. That means the model has correctly identified the classes. So in this case, in the first case, there are 9 samples of Setosa in your dataset, and model has correctly identified the 9 samples. In your second case, the true label is versicolor, and there are total 11 samples, but the model has only identified 9 of them correctly. So the model made 2 incorrect predictions for your versicolor class. And finally, for the Virginica, there are total 10 samples here, and the model made all the 10, and model predicted all the 10 to be correct, right? So that's how you ended up with 0.93 or 93% accuracy. So I hope the confusion matrix was clear. Sometimes it might take some time to get a hang of it, but you just have to compare each and every value. What does it mean? What does this 9 means, right? So this 9 means that the true value for this was Setosa, and the model has also predicted it as Setosa. So you have to understand each box in the confusion matrix and what does it mean. So now that we have built a decision tree model, we have generated the accuracy score, and we have computed the confusion matrix to get understanding of the performance of the model. Now let's quickly build the decision tree and analyze how the decision rules are inferred from the model, right? So for building a decision tree, I'm using a library called GraphWiz, which has a support to basically convert your model object of decision tree into a graphical format of how the tree might look like. So let me just run this piece of code, which will create the decision tree graph. So as you can see here, the first thing to note here is that, so when I said max depth equal to 3, it basically means that from the root node, it splits into three different buckets, right? This is the first bucket, this is the second bucket, and this is the third bucket. So it's not starting from the first node. It's basically after the first node, it is making splits into three different buckets. So that's how we ended up with max depth equal to 3. And also you might be confused by looking at so many components inside each node or each box. So let's try to break it down, okay? So first one is this is the root node, which consists of the most important attribute that the model splits on. So it is splitting on petal width. So let's use the if then else criteria to visualize the tree. So if the petal dot width is less than or equal to 0.8 centimeters, then if the value is true, then classify it as a Setosa class. If not, else we will go into the other bucket, right, where it again checks for a condition that if the petal dot width is less than or equal to 1.65, then if the value is true, then go into this bucket. If the value is false, then go into this node, right? So if the value is less than or equal to 1.65, then it predicting is that class is Virginica, but it's also creating multiple subconditions that you can further break the tree down. So we have again split the tree into two parts. So here again it is checking if the petal length is less than or equal to 4.95, then it is classifying the final outcome as versicolor. And if it is If it is not less than 1.65, then we look at this condition, and it's finally saying that this belongs to Virginica. So this is like a very intuitive way to understand how the decision tree model is making decisions, right? It is basically creating decision rules based on our input features, and it is classifying the values into different categories, whether this observation or this row belongs to Setosa class or Virginica class or versicolor class. So I hope this gave you a high-level understanding of how a decision tree might look like, and how we can visualize a decision tree. So this is basically the end of classification model walkthrough. Is there any questions that I can take at this point?
I think we can move on, but before that, maybe you can give us some context around Gini, or probably like we can talk about it at the end.
Sure,
Okay,
definitely.
people were also asking about hyperparameters and all. I think those things will be covered in the next session, so that shouldn't be a problem. But yeah,
Absolutely.
yeah, yeah,
So,
yeah.
so yeah, hyperparameters is one of the very important topic, and it usually takes easily one entire session to talk about it. So that's the reason we did not want to overwhelm you with talking about hyperparameters, but definitely it will be covered in the next session. But in this case, as you can see, max depth is one of the hyperparameter that I'm playing around with. I can even leave this out, but just to give you an understanding of what a hyperparameter is and what does it do. In this case, the max depth is basically controlling the depth of the tree, right? So when you say hyperparameter tuning, that means you can tune this parameter to have different values, right? You can have a depth of 3, you can have a depth of 4, you can have a depth of 5, and the model, and you can get a different model based on each value. So hyperparameter tuning will try to fit the model using different values of max depth and get the best model, which results in the best performance. So as Chanukya has mentioned, it will be covered in detail in your next session. So let me
Yeah.
talk about the other components of the decision tree node. So what is Gini? So Gini basically means like how pure is your node, right? It basically means that if let me just say one thing. If the value of gene is equal to 0, that means that your node is pure. That means all the classes in your node have been properly assigned to a single category. So in this case, to understand Gini, you need to understand what is samples and what is value in this component. So samples basically represent the number of observations that falls into this bucket, and the value represents the values for each of the class in this bucket. So here we can see that the value of Gini is 0. That means this node is pure. That means all the samples are properly classified as a single class. So the first value represents the value for Setosa, second represents value for Virginica, and third represents value for versicolor. So in this case, the model has said that based on all the 41 samples, it has classified it as Setosa. So it's a pure sample. That means all of the samples belong to a single class, which is Setosa. So if the so the goal of decision tree is to break down in such a way as to bring the value of gene as much as closer to 0 as much as possible. So that's the reason we once we have the value at 0, we saw that the decision has been made and the class is class has been identified as Setosa for this. Similarly, in this case, you can see that the Gini value is 0, and for this, all the samples were identified to belong to Virginica class, so it has been classified as this. In this case, again, the Gini value is 0, and all the samples are classified as belonging to versicolor category, so it has been classified. But in this case, if you noticed, there were only 4 samples, and only 3 of the samples are corresponding to Virginica, whereas one of the sample is corresponding to versicolor. So since you know that I've only split my data into max depth of 3, right, using the hyperparameter, it has stopped fitting the data further, right? So that's the reason, based on the majority vote, it has just said that, well, there were 4 samples, but 3 of them voted that it is Virginica, so I've predicted as Virginica. So this is how you can interpret a decision tree. Of course, when you do hyperparameter tuning, you can play around with your max depth, and you can further get closer to a Gini score of 0. So I hope that helps understand what
Yeah,
yeah.
definitely. I think that's a very nice way of explaining things. Thanks. Yeah,
Sure. Yeah.
yeah.
All right. So now that we have covered classification, we have some time to go over regression. And now that we have actually looked at all the different steps that goes into classification, the structure and format of the regression is very similar. So we will be able to cover it quickly. But if there are any questions, feel free to stop me. So for the data set here, for regression, we
Farhan,
had
before we proceed, I just wanted to give a heads up on random state. I think,
yeah,
yeah. But
sure.
that's fine. I mean, we can cover it in a regression problem. It is already there. Just wanted to give.
Absolutely.
Yeah,
Yes.
yeah.
All right. So for the data for the regression problem, we are dealing with Boston housing data set, which is basically a data set of different houses and the prices for different houses in the area of Boston, Massachusetts. I just put down all the columns because this data set is might look more complex than Iris because it has more number of features. So these are basically the features. You can read about them. But one thing I wanted to note is the target column, which is MEDV, which is known as the median value of the home. So just remember that the target column here that we are trying to predict on is MEDV. All right, so let's move on to the data import step. So here again we are importing pandas, and so here I wanted to like explain a new way of importing the data. So some sklearn library also comes with datasets class, which consists of several publicly available data sets that you can load directly and play around with. So in this case, this dataset was already available in the datasets library from sklearn. So I'm just directly passing in the method that will load the data into the memory, which is load underscore Boston. And one thing to note here is that when you load in this data, it will not be of pandas structure. So we need to convert this into a pandas data frame so that we can, you know, we can manipulate the data and play around with it. So for that, we first convert this data into pandas data frame, and we pass in the column names that we want to extract from this data set. And then we also need to explicitly say what is the target variable. Since we already know that the target is MEDV, I'm passing the value as MEDV here and getting the value and getting the target value in this variable. And then let me print the shape of the data set and the first five records for this data frame. So as you can see here, this data frame consists of 506 rows and 14 columns. And these are the 14 rows, 14 columns, which represents the input features, and your median value is your output column. So just by looking at your target variable, you can see that the values are continuous in nature, right? It's a numerical value which is continuous in nature, because the median value of house, it can be 20, 21, 22, 23. It can be any continuous range. So this is a classic example of a regression problem. So first thing is checked. We know that this is a regression problem. We looked at the target variable. Next, let's move on to understanding the data types and missing values. So let me print the info. So looks like I did not import this cell. So let me first import the cell, run this, and then let me check the data summary using the data frame.info method. So again, this gives us a high-level view of the columns, the non-null count, and the data types. So again, we can see that all of the columns here are basically float data types, which is the numeric data types. Okay, next, let's also check the null value counts. So we can see that there are no null values in this data set. We don't have to explicitly perform data imputation here. We can move on to the descriptive statistics. So again, as I explained the relevance of looking at the statistics of the data, let's print the statistics of the numerical features here. So again, like we can look at all of these input features and what is the corresponding mean value, standard deviation, minimum value, maximum value, etc. Using this describe method. So let's try to quickly look at what is the mean, what is the a median value. This is the median value of the home, and you can look at what is the mean value. So among our target column, the mean value is 22.5, right? That's the average value. And what is the maximum value? Maximum value is 50, and the minimum value is 5. So it gives you a quick idea about what are the different statistics about different columns in your data set. Similar to what we have seen earlier, we will also would like to print the count of values in your target variable. So let me print this. So here you can see that it could not print all of the rows because this is a regression problem. So you have a lot of values in your target variable which are continuous in nature. So basically it's an example of regression problem. And so we can see that the values are ranging from 5, 5.6, 6.3, so on until the maximum value of 50. Okay, so let's jump into splitting the data into training and test set. So here again, we are using the model selection library and calling train test split method and passing the data frame name, which is Boston in our case, and we are taking and we are using 20% of the data for our test set. And here I'm passing something known as random state. So I know sometimes people might wonder what the random state is. So it's important to understand. So basically, random state basically is telling what samples we need to randomly choose from our from our data set. So here, since I'm splitting my training data set into 80% and test data set into 20%, I'm specifying a random state, which means I'm going to filter only a specific set of random samples, and each time I run this random state, it will filter the same set of records from my data frame. So let's say I'm running this experiment now with random state equal to 1, and also you would like to replicate this notebook and obtain the same set of train and test samples. Then you can also use the random state equal to 1. It's just a way to tell your model that we want to filter only the fixed set of samples. We want to filter the same set of samples always when we pass a random state. So suppose I don't pass any random state. In that case, it will every time I run this cell like multiple times, 2 or 3 times, every time it only filters different set of observations from my data. But every time if I want to get the same set of observations, then I need to pass in the random state object. So I hope that was clear. And so once we, let's say, split our data into train and test, we are calling it Boston train, Boston test. Boston train is 80%, Boston test is 20%. And then let's print the shape of the original Boston data and also the shape of the Boston train as well as Boston test. And if you remember, as I mentioned, it's very important to reset the index so that the index value starts from 0 after you make the split. So let me run this cell and we can look at the shape. So there were total 506 rows. And after you split the data into 80-20, the number of rows in your train data is 404. Number of rows in your test data is 102. So let's move on to feature selection right now. And in this case, I'm going to give a different example of feature selection and not variance threshold. So this time I'm going to talk about something called as correlation matrix or a correlation coefficient. So on a high level, correlation matrix is used to analyze how similar are two features in your data set or how correlated are two features. So basically, correlation value so there is a correlation value which tells how correlated are two features. So a correlation value can range between -1 to +1. A value closer to -1 indicates that the two variables have a high negative correlation. Value closer to +1 means that the two variables have very high correlation or high similarity, and a value closer to 0 means there is no or very low correlation between the two variables. So let me run this correlation matrix. So we have a dot core method that we can apply on top of your data frame. So here I'm going to apply it on top of my training data frame to display the correlation matrix, and then we will visualize the correlation matrix. And then I'm using SNS, the Seaborn library, and I'm generating a heat map of the correlation matrix. So running this cell will basically print the correlation matrix where you can see that there are 14 columns, and then we also have a target variable on each axis, and this color coding basically indicates how correlated are two variables. So a value closer to 1 or color coding closer to the 1 means that they are highly positive correlated or highly negative correlated. So maybe let me give you an intuition about what features we need to filter out from the correlation matrix. So the features, we always need to filter out the features if only if they are highly correlated with respect to the target variable, or highly negative correlation, or if they have high negative correlation with respect to the target variable. Because if any feature has a high positive correlation with respect to the target variable, that means that feature is trying to explain the output better. Similarly, if your any of the feature has a high negative correlation, that means any increase in this feature will cause a dramatic decrease in your target column. So again, it is explaining, it has a relationship, it has a good relationship between the input and the output. So that means the value closer to -1 and value closer to +1 is of our interest to us, and a value closer to 0 is not going to help us, so we will not consider those features. So in this case, so in this case, I'm randomly choosing only 4 variables out of the 14 variables. But of course, there are there are intuitive ways that you can use to select the features. So in this case, I want to basically select top 4 features. So 2 of them has to have a high correlation with the target variable, and 2 of them must have a high negative correlation with respect to the target variable. So one thing that we can do is we can even print the correlation of each of the column with respect to the target variable. So using this piece of cell here, so the Boston core matrix is nothing but our correlation matrix that we created, and we want to find the correlation of all the input features with respect to the output column. So that's why we are passing MEDV here, and then we print this column. So as you can see here, for the MEDV, since this value is 100% correlated to the same column, it's 100, it's 1. Similarly, if we look at these two columns, RM and ZN has a very high positive correlation. So I will be interested to select these two features for my model. Similarly, the features PT ratio and LS stat, these two features have a low has a high negative correlation with respect to the target variable. So I will be interested to select these two features. So we are going to pick up the 2 high positive correlated features and 2 high negative correlated features, and use a model on top of that. Okay, so now that we have identified what features we are going to select, let's split our data into features and labels. So as I explained, it is important for us to tell the model what are our features in our training data set and what is our target label in our training data set. So here I'm passing in the feature values. So these 4 features, as you can remember, we selected from the feature selection. 2 of them are high positive correlated features, and 2 of them are high negative correlated features with respect to the target variable, which is MEDV in our case. And now let's just print the features and labels, and then create variables which will split the data into features and labels. And let me run this cell. So as you can see here, the data is split into features and labels for both the training data and test data. So now we would move on to the model creation for regression. Okay, so in this case, I'm going to take an example of linear regression, which is one of the most common regression algorithms out there. And let's look at the intuition of what a linear regression might look like. So simply put, a linear regression is nothing but a formula that you might be familiar with, which is y is equal to b0 plus b1 x1. So I'm sure like you must have heard about this formula in your high school. Like it can be like y is equal to mx plus b. It basically it represents the formula for slope of a line, right? So it's the same formula, and what it's trying to do is so let's understand the components in this formula. So y here means it's a dependent variable, x1 here means independent variable. Independent variable is nothing but our input variable, and dependent variable is nothing but our output column, and b0 and b1 are the coefficient values. So using the linear regression formula, we are trying to understand how the value of y, or how the output column is dependent on the input column, right? So this is what the linear regression model is trying to do. It is trying to learn the relationship between the output column with respect to the input features, and these coefficient b0 and b1 are the values that we need to find in order to get the best model. That means the model which can explain the value of y or the value of target variable very well using the input features x1. So here I'm just giving an example of a simple linear regression which assumes that your input feature has only one input column. But let's say since we have more than one input column, this formula can be interpreted as b0 plus b1 x1 plus b2 x2 plus b3 x3, where x1, x2, x3, so on are your input features. Okay, so this is so I'm just for simplicity purpose, I'm showing a simple formula here. And also I wanted to like give an example before we dive into the problem of how the model is going to build a linear regression model, right? So let's take an example of salary versus experience. So let's say we have a data set with input column called experience and sorry, input column called years of experience and output column called salary. Let's take this as an example. So here our input column is years of experience on our x-axis, and output column is salary on the y-axis. And we are trying, and these points represented by red are nothing but salaries of different persons, of different employees of a company. So as you can see here, what linear regression model is trying to do is it is trying to find the best fit line that can fit through all of the input points, right? So this is how the linear regression model is trying to predict the value of salary given the experience. It is trying to find the best fit line that can better explain what the input features mean. So basically, if we were to represent this formula y is equal to b0 plus b1x in the form of salary versus experience, we can represent it as something like salary is equal to b0 plus b0 plus b1 times experience, where salary is our dependent variable output column, experience is our input variable, and b0 and b1 are our coefficients. So the objective of linear regression model is to find the values of b0 and b1 that will best fit the line through the data points, through the input data points. Um, so yeah, I hope the intuition was clear. It might be a bit confusing at first, but I would highly encourage you to read through the notes here that I put in, which will also give you a more idea about the internal functioning. And definitely there is more math behind this, like how the best fit line is created. And there is something called ordinary least square method, which is used to find out the formula for best fit line. So I would encourage you to explore that if you want to read further. But this should give you a high level understanding of how a linear regression model works and what is the goal of the linear regression model. So with that, we can move on to the implementation step. So the first step is to import the linear regression model. So we can import it using sklearn.linear model library. And we call the model object linear regression, and we are saving it to LR variable, short for linear regression. And then we fit the model, linear regression model, on our training features as well as our training labels, right? So Boston train features consist of the training features, and Boston train label consists of your label column. And I'm going to run this cell. So this is going to fit the model on your training dataset, and the model now have learned the patterns from your training dataset. Now let's use this train model to predict it on the test features. Right, so we are going to use dot predict method on the Boston test features, and then we are going to create a data frame of prediction, so you can look how the predictions look like here. So let me run this cell, and here you can see these are the different prediction values. So for the first observation, it's 27.82. For second one, it's 28.17. So this is not by itself helpful. So let us compare side by side with the actual label as well as the predicted label. So in this cell, I'm going to combine the true label and the predicted label, and then print the data frame. So as you can see here, for the first observation, the true value or the actual value is 28.2, and the model has predicted to be 27.8, which is not bad, right? It's still close. For the second one, it's 23.9, but the model has predicted as 28, which is not that close. So this will, so you can use this piece of cell to visualize that how close is the model to the actual value. And um, and if you remember, I talked about the coefficient B0 and B1 that the model is trying to find out in order to fit the best fit line. So we can also print those coefficients. So let me, so the LR dot intercept is nothing but the B0 coefficient, which is a constant value. And LR dot coef underscore is nothing but the B1 coefficient, which is the value representing here the B1 in your formula, right? So let me run that cell and it will print the values for B0 and B1. So this is just to, just to understand from mathematical perspective, what is the best value of coefficient that the model has identified from fitting on your training data set. So now that you know that, let's go into the model evaluation phase. So how do we evaluate this model on a test data set? So there are different metrics for classification and regression. So for the regression, there are three main metrics called mean absolute error, mean squared error, and root mean squared error. So mean squared error is simply the average of the squared difference between the target variable and the actual variable, right? And root mean square error is the square root of the average square difference between target and the value, and mean absolute error is the absolute difference between the target value and the value predicted by the model. So here you need to understand what is the target and what is the value, and what is and the model is and the way we are evaluating is basically looking at the difference between the true value and the absolute value. So let's take an example of this prediction, right? So here the actual value is 28.2, but the model has predicted 28.82. So if we were to evaluate the performance of this single sample, so it's nothing but the difference between the actual prediction, actual value, and the model prediction. So that's what these formulas are doing with different cases, right? So let me implement these formulas and let's look at the numbers. So again, we will be using sklearn metrics library, and we will be importing the three formulas that we talked about, the three metrics, mean, absolute, error, and we will be passing in the actual test value and the predicted test label. Similarly, we will be passing the actual test label and predicted test label in each of the three metrics, and then we will print out the results. So as you can see, the mean absolute error is 4.28 for the overall test data set. For the mean squared error, it's 29.9, and for mean for the root mean squared error, it is 5.47. So these are the these results basically tell us how good is your model. So it explains the error rate between your actual predictions and the predicted values. And the model evaluation metrics in detail is going to be covered in the next session as well, along with hyperparameter tuning. So you'll get more understanding about the details behind each of these metrics for classification and regression. So with that, we have successfully completed our exercise of building your first classification and regression model. I'll be happy to take any questions if there are.
Great. Thanks a lot, Farhan. I think it was an
Thank you.
insightful session, and yeah, it went very well. Also, I think we have a few questions. Probably I'll pick some of them.
Yeah.
So, so there is this question which was there in between the session. What if the variable is finely distributed variable, and that small changes bring large differences in the target variable? Should we still drop that feature?
That's a good question. So ideally, if you have like a small variance between two features, it might or might not impact the performance of the model, right? So what I would recommend is not stick with one feature selection method, but maybe first run through the variance threshold, where you understand, where you filter the features which have high variance, or maybe if you want, if you still think that you might want to consider one of the feature which has low variance, that's fine. If you think it's important, you can keep it, and then build another feature selection algorithm on top of the remaining features. Let's say you can build a recursive feature elimination, or simply you can do a correlation matrix to identify the features which are highly correlated with the target, and choose those variables to use in the model. So I would encourage you to try, more than one or two feature selection methods, so you're confident about the features that you're using to feed it into the model. So I hope that answers the question.
But yeah, yeah. Also, there is one question on your work. So basically, can you request Farhan to guide us with a real life fraud detection scenario? What are the difficulties and in which way you handle it, or ways he process your data? Maybe you can. I mean, obviously,
Sure,
like,
sure.
some things would be confidential, but you can give a overlay. Yeah,
Of course. Yeah. So
yeah.
basically, fraud detection is a completely different landscape, and it's often known as to be one of the more complex fields of machine learning. But it's also fun because you're dealing with basically payments and transactions. So it might sometimes be fun working with the transaction data. So one of the most important challenges or pain points that I have encountered working on fraud problems is the class imbalance problem. So what is class imbalance problem? Class imbalance problem is basically when your target variable has a majority of classes as one category and only a fraction of them as another category. So normally fraud happens very rarely, right? So let's say you swipe a credit card you swipe a credit card on a POS terminal, and most often your transaction is often approved. Only in very rare scenarios, let's say you're trying to make a huge payment, or you're trying to make a payment from a different state or a different country, like the first payment, it might get rejected. So it's a very rare case that a fraud might occur. So whenever you look at your data set, your target variable might contain, let's say, 98 or 99% of your classes as not fraud, and only like 1 or 2% of your cases as fraud. Like in my cases, I've even seen like less than 1% of the cases as fraud. So how will the model learn from this data, right? Because the model will only learn more about the not non-fraud cases, because the 99% of the data set is saying non-fraud. So for this, in order to deal with this challenge and to overcome this problem, we need to do something called as sampling. We need to apply sampling techniques where we do either upsampling, where we like synthetically increase the minority samples, or we do downsampling, where we synthetically decrease the minority cases, so that the two classes, the fraud and not fraud, are equally balanced. So we have like 50% of fraud cases and 50% of non-fraud cases after sampling, and then you can use this model to follow the same steps, right? You can load the data, you can prepare the data, deal with missing values, deal with data type inconsistency, deal with duplicate values in your data set, um, and also make sure that there is no data leakage in your train and test split. So before doing any data preparation step, I always make sure that I split my data into train and then test, and repeat whatever the data preparation is done on the train, repeat the same steps on the test data set, and never coincide these two data sets, because we don't want any data leakage, because test data is basically you treat it as a future data. So everything that you do on this should be treated separately, and then you build a model on top of that. And usually, in our case for fraud detection models, we usually build decision tree or tree based models. It's not decision tree, so there are advanced models called as boosting algorithms like XGBoost, gradient boosting, etc. That creates sophisticated decision trees, and it can learn the patterns much better. And as you know, decision tree models are very interpretable. You can create a decision tree graphs and understand how the decisions are being made. So even that is very helpful for us to understand. So that's one of my favorite algorithms, decision trees in general, and the advanced versions of decision tree like XGBoost and GBM, and that's what I use more often in my job. So I hope this helped you get some understanding of my work.
Yeah, definitely, definitely. I think that's definitely valuable and insightful. And also, there is this question: why haven't you used R squared for model evaluation? I think for the a regression problem, maybe. Yeah.
Yeah, for sure. Yeah, so as I mentioned that there are quite a few metrics for each classification and regression problems. So for regression, I've only covered like three metrics which are most common, but adjusted R square or R square is also a popular metric, which tells you like how far is your predicted value to the actual value. But the reason I did not cover is because I did not want to overwhelm you with so many metrics, because I believe the next session is going to be on model optimization and model hyperparameter tuning, where the different metrics will also be covered in detail. So that's the reason. Are there any other questions, Chanukya?
Hello, Farhan.
Yes. Yes.
Yeah, I think we lost, or
Okay.
yeah, we
Is it better
lost.
now?
Yeah, yeah, it's better. It's better now.
Okay. Yeah, go ahead, Chanukya.
Yeah. Okay. So I thought, like, we lost the connection, so
Oh,
maybe
I'm
some
sorry.
of it might have been
Oh, got it.
lost.
Okay,
Yeah,
so
the
let me
last
repeat.
question.
Let me repeat one more time. So for the
Yeah.
evaluation metrics, the reason I did not use R squared is because I did not want to overwhelm with so many metrics, because metrics is itself another topic where you need to understand how each metric works, what is the mathematical formula behind it, and I'm aware that the next session is going to be on model optimization, where we will be talking about different metrics in detail, so it will be covered there. So I hope
Great.
that
Great.
answers
Perfect.
the question.
Yeah, that answers. And yeah, why didn't we do feature scaling here in different range?
Yeah. So let's say for this data frame, so what is feature scaling? Feature scaling, right? So feature scaling is when some of the features are having values in different ranges compared to other features. So in this case, the reason we did not do feature scaling is because like the focus of this experiment was to build a classification and regression model, and at the same time, I did not consider this feature for my model. So in this case, if you look at this data frame, only two of the features seem to be on a very different scale, which is tax and B. And the reason these features are not scaled is because from the feature selection, we identified that these two features are not coming out to be very important. So we haven't like scaled these features, and instead we use the top two features from high, which had high positive correlation with the
Coming out to
target,
be very
and two
important.
with
So we have.
high negative correlation with the target.
Yeah. Okay. So we have another question. I think okay, so there is upsampling isn't good based on many papers, and downsampling make may I mean we'll lose a lot of patterns because we delete the data sampling. So what is the better method to handle based on your experience, sir?
Uh,
So
so, so actually, yeah. So this question mainly depends on the data availability, I would say. That's the primary factor. So let's say you have a huge amount of data, right? You have like a million of records, and you don't need to worry about losing the data, right? Like, because you can train a model even with 100, let's say 100K samples or 500K samples or 1 million samples. So when you have a high set of data, a high number of observations in your data set, then you're okay to do downsampling, because even though you're basically reducing the number of rows in your data, but you still have a good amount of data that you can still build a model with. But let's say if you have already you're short of data, you only have let's say 100K records, and you don't want to lose any more records, then in this case downsampling might not be a good idea, because you have a risk of losing the information, and the model might not be able to learn all the patterns from your input data. So in that case, I would recommend you to try oversampling. Oversampling is when you're trying to increase your minority samples, increase the number of observations in your minority samples. So oversampling, in my experience, I usually use downsampling technique, because there's always availability of data, and we deal with a lot of payments data. So as you can imagine, PayPal deals with so many transactions. So I don't find it any problem going with downsampling, because even after downsampling the records, we still have good set of information that we can use to build a model. So I hope that helps.
Yeah, definitely. And what evaluation metric do you use for class imbalance? Maybe F1 score, or yeah, maybe you can.
Yeah. So,
Yeah,
as I mentioned, accuracy is a general metric for classification, but when you're dealing with a class imbalance problem, accuracy is not a good metric, and it should never be used. Because let's say I have 100 observations in my data set, and 99 of those observations are corresponding to not fraud, and only one of the observation is corresponding to fraud, and your model is predicting your entire data set, all the 100 observations, to be not fraud. So in this case, you get an accuracy of 99%. But does that necessarily mean that your model is truly 99% accurate? No, right? Because it has missed the one important transaction which was supposed to be flagged as fraudulent. So in this case, you might need to look at some additional metrics like precision, recall, and like F1 score, which is the harmonic mean of precision and recall. So precision and recall are the two of the most commonly used metrics that I always look at when dealing with the class imbalance problem.
right. And someone is asking, do you think privacy preserving AI will address the data leakage in industry?
I mean, this is a very challenging question, I think.
Yeah,
So
yeah.
if did you say privacy data science?
Privacy of basically the question is, let me check again.
Yeah.
Please, do you think privacy preserving AI will address the data leakage in industry?
So I think to some extent, yes, like from my limited understanding. So because privacy is an important factor, especially when you're dealing with AI problems related to financial data or some critical data that might cause issues if it is exposed to the outside world. So to some extent, I think it helps to control the data leakage of such cases. But I think there is not one straightforward answer that I can think of for this question.
Yeah, got it. Aligned. And yeah, I think that's pretty much with the questions. And thanks a lot for Han for the amazing session, and thanks a lot to all the audience and also the coaches out there, Tanmay, and I think there are a few other Manish and Gunika who were out there, like addressing a lot of questions. And
Yeah.
on final thoughts, Farhan, maybe you can share about your experience uh, to the journey as a data scientist, and any inputs or any thoughts that you have for the learners.
Sure, definitely. Basically, when I started my data science journey, it was not so long ago. I would say about 2 or 3 years back is when I came across this field, data science, and there was a lot of hype going on around. And I was interested in like data analytics. Like I was fascinated by the data in general and wanted to get a deep dive into the data field. So that's when I approached the data science, and but it was very challenging for me, especially when I was starting out, because there was no fixed curriculum that you need to follow, and even there were not enough job opportunities out there. It was just starting out basically. So for me, it was more about exploring what is data science, what tools do I need to learn? Do I need to learn Python or R, or do I need to focus on the problems? So there were a lot of open questions. But and then it was a wild journey, I would say. I had to take a lot of open source courses. But one thing that really helped me is, at that time, like 2 years back, I was working in a financial company, and though I was not in a direct data science role, uh, whatever I was learning on my side on data science, I started applying that onto my work. Since I was working in a financial company, I was dealing with financial data. So I started using that data to build machine learning models to get an understanding of what real world data might look like, right? And how I can get intuition from building models on real world data. So this is what I would encourage you, no matter what field you're in, no matter what journey no matter what area you're currently working on. try to see if you can apply data science in your role, because data science is a very broad field that can be applied to any problem. It can be applied to wide array of problems. So try to see if you can apply whatever you're learning from this session or from the boot camp or from outside, whatever you learn, try to apply and see how it looks on the real world data. Try to get a feel and hang of the data out there, so that will give you some confidence when you want to go for an interview, or when you want to apply for a job, or when you want to solve a real world data science problem. So I think that's one of the important tips that I want to share with the people.
Yeah, totally aligned. Thanks a ton for that, Farhan, and
Sure.
keep doing the amazing work. I think you've been a great coach, and also a mentor for me. Thanks a lot for all the contributions,
Yeah, thank
and
you for having me. Yeah,
yeah,
thank you for
thank
having
you,
me.
and
Thank you.
yeah, take care, and thanks a lot.
All
Yeah,
right, thanks
bye.
everyone.
Yeah,
Bye.
bye.